Oh, hi. So this is another video in the PolyWalk series, and what I've done in this is you can see that these triangles, they rotate now, they don't slide. So I built a little animation algorithm, and so I'll play this, maybe zoom in, that you can see these triangles flip out, and what it does is the triangle, let's see if we can get a good version on this one, and they go transparent, so they fade in. We can see that on the alpha. You can see how this new triangle, it basically takes the shape of this triangle and then it rotates into position, and they all do that. There's a couple additional features that I want to make where they all flip from the outside, like on top and out. I think they all go different directions depending on the angle, because the rotation is built from the difference between the two angles here. So I'm going to quickly go through and talk about what we did. So I'm just going to wireframe it and then put up the alright, so it's right here. It's called flip, and this is the other one. It just slides, and so I did have to, so, you know, the original polygons, they don't have somewhere to flip to, so what I did is I just used the old algorithm in here. So it's pretty lengthy, and so what we have to remember is, let's see, let's grab a polygon right here. So let's look at this guy right here. So this triangle, this bright yellow triangle here, let me just get a better pointer and zoom in. This triangle talks to that point with that ID. And the way we did that is we did that here. Promote the PRID from the last, which is right here, from the last vertex, and then get the opposite vertex. And so what we need to do is we need to know the opposite triangles. We need to know this triangle, compared like with this primitive, its opposite vertex, which is right here. And so we need to do the same thing, but we promote from the bottom, and we promote a parent PRID, so that's a parent triangle, and then an opvert parent. And so this triangle knows, actually I'm gonna take off alpha. Oh, I should have alpha off. Oh, wait, no, I bet you I put it in here. So alpha in here. So it's a pretty lengthy working out these rotations. So you can see how this one, he's sliding into that. He sort of like disappears here, and you know, because he's going pretty quick, and then that transforms. So you can see, here's actually probably a better example. You can see right on here, and they flip as those go. And it's all no simulation, as you know, and so that's, I think, a pretty big speed benefit. Alright, so I think I use this function, not as much as I should. So what we got to do is, for every triangle, I'm going to walk through the logic of this, find the PRID. So this triangle is going to talk to that point. Alright, and then we want to get the primitive, or at least this primitive right here. This is talking to this entire primitive, right? This triangle is talking to that primitive, that polyline. Alright, so we're going to get the opposite vertex that we promoted, and so that's this point right here, because it's opposite of that interface. And then we get the blend attribute that's, you know, allowing our polylines to grow. Alright, so the next thing I do is I get the position right here to use later. And then what I get is the parent ID and opvert parent. And that is coming from basically the bottom polyline. So it's this triangle. This triangle's opposite vertex, and this triangle's primitive. So it's this triangle here. So, and we're operating, remember, this flip is operating on the triangle mesh. And so what we do is we get with this is the standard vertex index, vertex point, and then get the point position. So we're getting that position, the opposite position. And then basically what we have to do is we got to compute the pivot in between these two triangles. So the way we do that is, because we have this opposite vertex, we can run this formula, and that's going to get us this vertice and this vertice. And then what we can do is I am using this formula, and that's just vertex ID, vertex point, returns the positions of these two, and then we average them together, and then we get a point in the middle of here, right on this line we get in the middle. And so then what we can do is we can build a rotation matrix, because what we can do is we can get this center point and this center point. What I'm doing is I think I'm building these two center points, which is, I think, okay. I might want to build it from the center, but I get a vector from here and then a vector from here. So there's a vector built here and a vector built here. I think I'm going to change that. I think I am going to change that. Oh wait, no, this is the interface position, sorry. Oh no, I do that. So there's the pivot right here. And then the child vec is this vector, so this point minus that point. And the parent vec is this point minus that point. And what we do is we use this function called a dihedral. And since we give these two vectors, we get a rotation matrix that will take the child vector multiplied by the rotation matrix. That will rotate the child onto the parent. So this is basically doing our rotations for us. And so that's called the dihedral. And it's adding some complications because, I want these to all rotate a certain way, flipped up, so I'm probably going to have to revisit this. And then, so what I'm going to do is to blend the rotations, I'm going to turn them into a quaternion. So I'm going to convert this matrix into a quaternion. And actually probably just I could probably just move that into there. I don't think I need R1 again. And then I have to make a zero quaternion, or just a quaternion identity. I'm not sure what you call this, but that's just basically no rotation. And then so here's the blend. So the blend is taking the attribute from here. So as this thing grows, that's our blend attribute. And it's going to blend the rotations between fully rotated and not rotated at all. So what that basically is, that's the rotation matrix from here over to here. And so what we're going to do here is the logic behind this, to make these rotations work properly, you take this position, you subtract the pivot, then you rotate it, and then you add that pivot back in. That's how rotations work. You have to have a pivot, and you subtract from that position. So it's this vector minus this vector, rotate by the quaternion, the slurper, and then add that back in. And that's right here. So this is our rotation blend. Slurper just sounds funny. All right, so once it rotates back, it's going to rotate. We need an initial position here when it's going to here. Now, to get it to this position, it's a little bit tricky, because what we got to do is we have to first set like a rest, and then we have to, so it rotates that vector around, so it's not going to be aligned. And then we take the parent position with that rotated vector, and it's something like it might be out here, might be out here. So there's a difference of a vector where it doesn't line up perfectly. And what we do is we just compute that vector called dd, and what this is just the difference between the offset of the shape. And then what we do is we make another, it's basically, this is the inverted or the opposite of this rotation. Because as this thing goes, we need to rotate that difference vector along with it. And then so that's what we do right here. And then we blend it off and then add it to the position delta. And then basically if it's not a root primitive, if it's not a starting triangle, rotate it. And then for the starting ones, we just put the original, this is just the original slide code in here, and that's it. And just delete the primitives if there's no primitive yet. And that is rotations. So thanks for watching. I'll probably tweak this up. Next, I'll probably be making some controls to make this a little bit easier to use. Some adjustments up on the top level. So basically hooking up, these the proper parameters up here on how so we can tweak this thing. All right, thank you for watching.